Yeah, I was actually wondering where the light switch is. If they're hidden behind this thing? Okay. This way. Huh. Oops, those are raising the sunshades, which is really cool, but not what I wanted at all. Oh, well. That might be easier. Hopefully the rays of the sun will not hurt us. Okay, so I guess I'm going to get going. So what I want to start doing now, so where are we? We got to the point where we talked about K0, we talked about K1. What I want to do now is bring in the homotopy theory, which there hasn't been all that much of if you think about it, in sort of two directions. One of them has to do with taking input that is homotopical, and the other one has to do with taking or producing output, which is homotopical. And we'll get to both of those today if all goes well. But I want to start by doing a discussion about abelian categories. In part because, as one of the sort of philosophical points I want to make, or yet another slogan, abelian categories, and more precisely the proof of the Freid-Mitchell theorem, are a place where you see a philosophy about enriched categories being a way to translate notions of homotopy theory, or in this case, notions of algebra around. And you started to see the beginning of this yesterday, right? There was a talk about the Dwyer Con simplicial localization. Now, I should say that the Dwyer Con simplicial localization and the hammocks that were drawn, this is somehow a window into divinity. The fact that this exists and works is really surprising. And as you continue to study homotopy theory, you will be more and more surprised by the properties of this if you have the pleasure of working with it. But anyway, so I'll come back to the Dwyer Con simplicial localization, but let's start by talking about abelian categories. And really what we want to start with is, we'll start with additive categories. And with additive categories, so what is that? So we'll say that C is additive if C is enriched in abelian groups, aka Z mod, and C has a zero object and a product. Okay, so I mean the categorical product. Now, let me talk about these conditions a little bit and remind you what these things mean. So, to be enriched in abelian groups, so C is enriched in Z mod means that for X and Y, in the objects of C, we have a composition map like this. Well, first what it means is that CAB is an abelian group, and moreover, we have a map like this, which is a group homomorphism, right, which is a map of groups. And this is coherently associative and unital. Okay, and you might wonder, why do I write the composition in this order? It's because of the way people choose to write composition. Right? There's a funny thing about how the order of that works, and that forces this notation. Okay, so what you should think of with an abelian group, or this says something kind of interesting, which is that one of the things that we'll use about this is that we always have, for any category, we have the Oneida embedding. Right, so for any C, I can map C into functors from C up to sets. Right, and what do I do? What this is, X goes to, hom in C from blank to X. right? This is the Oneida map. And what's kind of cool is that, and the Oneida lemma says that this is fully faithful, but what's sort of cool is that in this case, what it means to be a category enriched in abelian groups is that we have the following version of this. Where we can look at functors into abelian groups, which is, and it's the same thing, right? X goes to Hom C blank to X. And in general, we're interested in both the representable functors, and we're also interested in what are called the co-representable functors, which are just maps in the other direction, right? This is a covariant embedding. This is a contravariant if you take embedding. But both of these are interesting. Maybe I'll give these names. These are representable. These are co-representable. And let me give you some, so this is a very beautiful construction, and let me give you some algebraic motivation for what this is. So another way to talk about having an enrichment in abelian groups is to say that you're a ring with many objects. Okay? So a category enriched in abelian groups is a ring with many objects. And I think this terminology, well, I learned this from a paper of Mitchell. I don't know from the 60s. I don't know if it predates that. But in any event, why would you say this? Right? What makes you say that this is a ring with many objects? Well, think about the most simple example where you have a single object. Right? What is a category enriched in abelian groups with a single object? It's a ring, right? You know, what do you have? If you have one object, I have my group, and I have a composition map. So, and the composition, gives us the ring structure. So, in this perspective, what is this? Well, what's an additive functor from the one object category to Z modules? You pick out a Z module and you have an action of the Hom. That's a module, right? And so you want to think of this as modules over our generalized ring. Okay, so this suggests if you think about fun C-op grouping in groups as modules. Okay, so we're going to come back to that perspective and make it precise. And one of the things that I sort of keep saying is lurking behind everything is that all of the categories, we always want to sort of think about the categories that are relevant in algebraic K-theory as some kind of module category. And the first version of this comes up for abelian categories, where what we'll prove is that any abelian category is a full subcategory of a category of modules. Okay? The ring is C, the additive category. It's modules. Yes, thank you. Maybe I should write that. Okay. So, and what is this kind of map? The inclusion is something like the map that takes a ring to itself as a module. Only the ring has lots of objects, so you have to use lots of representable functors. Okay, so now we want to insist also that we have a zero object. Remember, zero just means initial and terminal, and that we have the Cartesian product. So we require sort of some minimal limits. And in that case, one thing you know is that in fact you also have coproducts, and coproducts and products coincide. Right? This is an exercise. So an exercise is that in an additive category, finite products and coproducts coincide, and we tend to write that as the direct sum. Okay? So now I want to say something about what it bought us to have this picture. Why am I bringing up the Yoneda lemma? Well, one of the things you want to do, so what do I want to do? What is the slogan? Maybe I should actually write rather than say things, but what we want to do is axiomatize, right? Sort of our goal somehow is to axiomatize a setup to talk about exact sequences, and in particular, kernels and co-kernels. And if you've studied abelian categories before, or if you think about it, of course you can write down some properties of being a kernel or some properties of being a co-kernel. Now, I'm not going to do that. Instead, I want to give you a different definition in terms of the Yoneda embedding. And the point is the following. If what are we modeling? We're modeling the situation that we understand in the category of Z modules, or R modules, where we know very well on a point set level what we mean by a kernel and a co-kernel, right? And now we're going to translate that into the setting of some arbitrary category by using the mapping spaces. And I want to emphasize this because this is the fundamental move of homotopy theory at some level. What the Dwyer Con simplicial localization tells us, and what's been radically and massively exploited by all the people thinking about infinity categories, is that if I have mapping spaces which are simplicial sets, if I have mapping spaces, well, if I don't understand homotopy theory on spaces, I'm in a lot of trouble. But that's where we think we understand it best. And we can translate notions of homotopy theory from spaces to arbitrary categories via the mapping spaces. And in some sense, via the Yoneda embedding. And this is the hypothesis. So this is a sort of first version of that. So let's make a definition, which is to say that if I have f from A to B in an additive category, let's call it C, and let me make sure I write this properly so I don't screw this up. Yeah. So the kernel of f, if it exists, right? It might not have a kernel, but if it has a kernel, the kernel of f represents the functor kernel of Hom from in C from blank to A via F, or F star, Hom of C from blank to B. Okay? This is a functor, right, from C to abelian groups. And I know what the kernel is in abelian groups. And if that functor is represented, the representing object is what we call the kernel. Okay, now again, I want to emphasize how cool this is. Right? Well, I've taken the place where I know what kernels are and translated it into a place where they don't make any sense, and I haven't had to say anything else about sort of various kinds of descriptions of the properties of the kernel. It all comes from sort of things I already know about groups. Now, an excellent exercise, which I highly encourage you to do, and some exercises are about algebraic K-theory, and you should do if you care about algebraic K-theory. This exercise is a general life skills thing. It's hard to imagine, I guess maybe if you're doing analysis, but maybe then you wouldn't be here. If you're here, you're probably working in enough of an algebraic context that you should do the exercise of checking that this has the properties of the kernel that you expect in an additive category. Okay, so check this agrees with the usual notion. Similarly, the co-kernel co-represents the functor kernel Hom C B blank. I wonder if I got the stars right. Hom C A blank. And I mean to write kernel there, not co-kernel. And again, yeah. So it probably doesn't exist in that case, right? So the kernel, right? This is a map of groups, right? And that has a kernel. So then, are you happier? Okay, let me. Yeah, I mean, you don't, right, this is, so if in the event that the representing object exists, then that's what the kernel is, but it might not exist. And what I'm about, R modules. Right, no, like, let me say that differently, sorry. Yeah, so I should be giving examples. So the additive categories that we're interested in are, for instance, proj R, or free over R. These are subcategories of an abelian category, namely R mod, in which so an abelian category, I'm going to write this now, is distinguished by having every map has a kernel and a co-kernel. Most additive categories, not all maps do. You know, and you can think, I mean, well, there are lots of ways to think about that, but let's leave it at that. So, right. So, example of additive categories of interest are proj R and free R. Now, if two conditions, first, every map has a kernel and a co-kernel, and two, let me get a little space for this. So, if I have a map F, once again, what are we calling our object, A to B, if I have such a map, now if I assume that every map has a kernel and a co-kernel, well, what I have is I have the kernel of A, the kernel of F, and part of the exercise, incidentally, in thinking about, maybe I didn't articulate carefully the exercise is to line this up with the usual notion and, for instance, to extract the universal property of the kernel from this description. So the universal property has to do with having a map to A that obeys certain properties, right? So anyway, so we have this map to A, we have F, we have B, we have the co-kernel of F, and now I can take the co-kernel of this map, right? And I never remember if that's called the image or the co-image, but anyway, so this turns up, let's just take co-cur of, let's give this map a name, let's call that alpha, let's call that beta, co-cur alpha, and there's also here, there's the kernel of beta. Sorry, this diagram is looking a little skewed, but anyway, we have these things, and if you think about it, and this is another good exercise if you've never seen it, there's a map like this. There exists such a map, and if that map is an isomorphism, this is an abelian category. And if you think about what these things are saying, that map is always an isomorphism. I mean, or in the example that you know about, namely R mod, you can calculate directly that that map is an isomorphism. So let's call that gamma. And we'll say if every map has a kernel and co-kernel, and 2 gamma is an iso, then we say that C is an abelian category. Okay, so, and this sort of condition is something like asking that your category has limits and co-limits. It isn't, but it's that kind of condition, right? We're asking for having categorical constructions for any map. Okay, so now I want to state the Freid-Mitchell embedding theorem, which makes use of the now erased, I guess, additive Uneda embedding. So, theorem. Freid-Mitchell. And let's say that A is a small, this is not the strongest form of the theorem, but it's good for us. A is a small, and I shouldn't call that A. C is a small abelian category, then C is a fully faithful, well, let's just write this as C is a full subcategory of R mod for some R, and the embedding is exact. And what does exact mean? Exact means it preserves kernels and co-kernels. Okay? The embedding is an exact functor. So what this says is that any abelian category looks like a piece of a module category. So if you if you've ever done any homological algebra, this is at the heart of why diagram chasing works. Right? When you chase diagrams, implicitly the reason that that's working is that really it's like you had elements, even though you sort of don't. So this is a beautiful theorem, and there's a nice, you can ask the question, so it's a full subcategory, that's great. When is it actually a module category? And this is closely related, once again, to the talk on Morita theory. So there's an extension of this, which is that C is equivalent to the category R mod if C has colimits and C has a compact projective generator. Okay, so let me explain those conditions a little bit. So what, has colimits means what it means, but let me talk about what a compact projective generator is. So, I'm sorry? Don't all abelian categories have colimits? No, they don't have all colimits. They have coproducts and... Yes, they have finite. So all I stipulated so far is the existence of finite coproducts and products. Finite. Yeah. But here I want, for instance, countable coproducts. And in fact, we'll use that in the description of compact very shortly. So, okay. So what does this mean? Well, let's consider where do these conditions come from. R mod has a distinguished object, right? What is the distinguished object in R mod? It's R, right? And R has a special property, right? Any module M admits a surjection from R to the n for some very large number n, right? Possibly infinite, right? But if you take enough copies of R, it surjects onto anything. And this is what it means to be a generator. So we'll make a definition, which is that R is a generator if any object admits, God, I shouldn't say R, I'm sorry. M in our putative category C is a generator if any object admits a surjection from copies of M. Okay, and projective means the generalization of projective in the usual case, namely in terms of the lifting property. And what does compact mean? So compact, and we used a fact like this yesterday, I think. So compact, you might wonder, what does compact mean algebraically? And compact means that Hom C M blank commutes with infinite coproducts. I mean, really, you might say this is commutes with filtered colimits, but in this context, this is enough. And what that means is that any map into an infinite coproduct kind of lands in a finite piece of it. Right? That's what that means. And that's exactly the property that you know and love about compact spaces, for instance, or a property that you perhaps know and love about compact spaces. Okay, so, and it's a thing you can check that this is true for R, for instance, in the category of R modules. Okay, so how do we prove the Freid-Mitchell theorem? Well, let me give you a sketch. So the idea, what should I do, right? You should now know, just based on what we've said, sort of what the basic idea ought to be, which is embed R in its category of modules, right? So let's look at, or rather C. So what do? We look at, well, in fact, we look at C into functors from C up to abelian groups, right? And this is not bad. This is like a module category, as we've discussed. But we would like to, but we need to worry about having it be sort of a module with a single object, not a module with, not over sort of many objects, at least for the purposes of this theorem. And so the way we look at that is we actually, let me make sure I get the ops right. It would be a shame to lie about that. Yeah, so what we want to do actually is look at C op into functors from C to abelian groups, which is the same thing, right? And what you now observe is that the image, so this is X goes to Hom in C from X to blank, right? That's a covariant functor. And this op, flips the functoriality here. So it says it's contravariant here, and it lands in covariant functors here. And now the thing you observe is that, and you know this, again, if you know any homological algebra, is that this actually lands in left exact functors, right? It takes short exact sequences to things where there's a 0 on the left. So what we really do is we restrict. So we really look at C C op fun C to abelian groups. And now we factor this through a category I'm going to call L, which is left exact functors. And now what you check, and this is not easy. So in the sort of level of our exercises, this is an exercise you could do, but it would be a substantial project. You check that L is in an abelian category. And it's, in fact, it's a very nice, it's called a Grothendieck abelian category. So it's a particularly nice abelian category. So L is fact. L is an abelian category. In fact, it's a Grothendieck. And moreover, L has a generator. So what's the generator? So that's great. Like now I'm sitting in an abelian category, but I'd like it to be a module category. And what, I had an abelian category to start with. So what's the generator of L? I'm sorry? What's more than that, right? So Hams out of R is the generator if you had a single object. Right? But now I have a lot of objects. But that's fine. I assumed I was small to begin with, so I can add them all up. Right? So the generator of L is the direct sum over the objects of C of Ham in C Z blank. And it's an exercise, and again, this is an exercise you can do to check that actually surjects onto everything, right? Or copies of that surject onto everything. So that's our generator, and let's call that what do we want to call our generator? I don't want to call it R, but let's call that G. And so finally, how do you extract the ring? So if I give you the category of R modules, and suppose I tell you that it's R modules, and I even pick out which module corresponds to R, so I give you a compact generator, how do you extract the ring? You look at the endomorphisms of that object. So if I look at, so R in the theorem equals the end in L of G. And now you check the conditions for, now you check that this actually turns out to be injective, and we work with L up to get something that's projective. So there's more work to do to finish the proof of the theorem, but sort of the idea is that I want to communicate is that you embed into some piece of this generalized module category, and you recover the ring as endomorphisms of the generator. Right? Those are the two ideas from this proof that I want you to remember. That's the story.
What is the generator again?
It's the direct sum over all the representables.
So, what are you varying Z?
Varies over the objects of C. Right? So if the ring had a single object, it's just R, or Hams out of R. But if it has a lot of objects, I just add all those things up. I'm sorry? Right, this is not, no, this is never going to be compact. Yeah, that's not really consistent with what I wrote down. You can check, and it's not that bad to check that this is injective, and so in the opposite category, this is projective. But of course, this is not going to be a compact generator, even though you assume you have a set of objects. So I'm misstating this slightly. Damn. What do I actually want to say? Let me see if my notes will help me. Yeah, this really doesn't feel like it ought to be a compact object. No, this is definitely, so I apologize, I'm botching something. This is definitely this is the argument, and this is definitely the generator you want. This is your ring, and you definitely find that L is equivalent to, L is equivalent to this category of, I think this actually is compact because we assumed the category was small, right? And I think that set theoretic condition actually saves us. But now that I say that, that sounds fishy. So as not to derail the lecture, let me defer this point. I could leave it as an exercise, but no. I'll figure this out. I'm sorry. But okay. Anyway, this is something like this is the argument. Yeah. So what we did is the following. We started with some abelian category, and I want to embed it in a module category. And my first guess is just the functor category, the pre-sheaf category, right? But the pre-sheaf category doesn't have such good properties. It has fabulous properties, but it turns out that we actually land, if you think about it, in left exact functors, and so it makes sense to restrict. You discover that it makes sense to restrict to the full subcategory of left exact functors in here. That then turns out to be a Grothendieck category, which I'm not defining, but means it has particularly nice properties, and we can identify a generator in there. And and then we check, and this is you can do it. That's an injective generator, and I guess I'm asserting that's a compact generator, which for reasons that are causing confusion. So anyway.
You call it the pre-sheaf category or the covariant functors? Sometimes the
Yeah, you could call it co-presheaf if you want. Or what I should say is that you're right. Traditionally, the presheaf category is functors out of C-op. So this is the opposite of the presheaf category or something. I guess it's not that either. Let's call it the co-presheaf category. OK. So having done all of this, I now want to make another definition. So definition, which is that we'll say that C is an exact, so what's the advantage of abelian categories? It's that abelian categories tell us about exact sequences. And so what I want now is that C is an exact category if C is a full additive subcategory of an abelian category. And we're going to say the data of an exact category equips us with a notion of exact sequence. And so we'll say where, let's not use A anymore. Let's use x to y to z is exact in C. Let's give this abelian category a name. Maybe we will call that A. Is exact in C if it's exact in A, right? So we just inherit. And we're also going to say that C is closed under extension. And what I mean by that, this is a sort of useful technical condition, which means that if we have x to y to z now in A such that x and z are objects of the subcategory, then so is the thing in the middle. And if you study the subject, one thing you'll notice is that you can give, of course, an intrinsic axionization of what it means to be an exact category. And in fact, Quillen did. But it reduces to this. And this is sort of an easier way to, or a more concise way to describe what the properties we want are. So now, as you might imagine, but maybe I just say this as an exercise, we can define K0 of an exact category. Right? We've already sort of talked about how to do this. OK, so now, so we've done all this work to set up this theory. But now, what I want to really say is that this isn't good enough. It was all a waste of time. No, I mean, it was, what the issue is this, which is that the perspective that I want to shift to is that I now want to start talking about homotopy theory and homotopical categories. And exact categories are wonderful. I should say that Quillen developed a very beautiful theory of the higher K theory of exact categories, which I encourage you, if you're interested in, to study. I'm not going to talk about it, however, yes? Yeah, yes, thank you. Right, there's this great theory of the K theory of exact categories, but this is too algebraic. So I want to say the following thing, which is that, proj_r is an example, right? I mean, all of proj_r sort of is always our example, at least for now. But we're now going to shift to something different, which is that exact categories are too small to do homotopy theory. So in general, maybe what I'll say is, Armond is too small for homotopy theory. And what I mean by that is that I want a framework in which I can set up, I want some sort of abstract framework for homotopy theory in which I can make sense of homotopy limits and colimits, and I can make, for instance, I can make sense of mapping cones and cylinders and things like this. And it's not sometimes there are things you can do if R is very special. But in general, you can't, in the generic setting of Armond, that doesn't really make sense. But we know, following Grothendieck and his school, there's a way algebraically to handle this problem, right? If you want homotopies and you want to work in algebra, you pass from R mod to complexes. Let's say bounded complexes, or R modules. Well, let's not even say bounded. Chain complexes of R modules. And now the point is that this has homotopy theory. Always. So, but I want to make this precise. So it's all well and good to say has homotopy theory. And if you know anything about the category of complexes, you sort of maybe know what I mean, right? You know something about how to define the mapping cone, probably. It has an explicit construction on complexes, or what chain homotopy means, right? I mean, these words have that name for a reason. But I want to now introduce a sort of concise framework for talking about homotopical data, which is due to Waldhausen. So this now will lead us. And what I'm doing as usual, so I should give you some context. I keep introducing these sort of new structures on categories, right? Exact categories, or we talked about categories of symmetric monoidal products, or categories with exact sequences of one sort or another. I'm giving you sort of minimal sets of data, scaffolding you need to define algebraic K-theory. So in some sense, this is going to be our more or less final piece of scaffolding. Well, for us, it is the final piece of scaffolding. In general, you can weaken this further in a way I'll allude to. But let me talk about now Waldhausen categories. So the idea is that this is going to look like this should look like a piece of a model category. So it's going to be a category C with distinguished subcategories, which I'll write as the cofibrations in C and the weak equivalences in C. And I'm going to have some properties on these sets of maps. So what are the properties I might require? So what do I want? I also want to assume that C is pointed or has a zero object. And now what I want to assume is that the isomorphisms are in cof C. The initial map, and I'm going to decorate my cofibrations with these pointy arrow symbols. The initial map to any object is in the cofibrations in C. And most importantly, if I have a diagram like this, where this is any map and this is a cofibration, then I'm going to require that the push-out exists. So far I've just said I have some subcategories of maps. But now what I want to say is that the push-out exists. And what we have is a diagram, of course, that looks like this. So the push-out is Z, push-out over X, Y. And I'm going to require that the cobase change of a cofibration is a cofibration. So that this map is also a cofibration. And now I'm going to require, and I'll tell you something, I want to give you an conceptual interpretation of what we're doing in a second. Let me finish telling you the axioms for the weak equivalences, and then I'll tell you what this all means. So, cool. And now what I want are that the isos are weak equivalences. You don't have to, but I'm going to assume for convenience that the weak equivalences satisfy 2 out of 3. You can do this without that. Maybe I'll leave that out. Let me just say, often, the weak equivalences satisfy 2 out of 3. And the other thing about the weak equivalences is a gluing axiom, which is that if I have a diagram like this, and one of these maps is a cofibration, and I have maps like this, and those maps are equivalences, then there's an induced map. The universal properties give us an induced map on pushouts, and I'm going to demand that that be a weak equivalence. So point-wise weak equivalences, if you're pushing out along a cofibration, get taken to induced weak equivalences like this. Okay. And what this is this So let's make some observations about what this data tells us. So first off, one thing this says is that that category C has finite coproducts, right? So let's observe C has coproducts, right? Because if we take the point, that maps into X into Y, and now we've required that the pushout exists. And what that is the coproduct of X and Y. Okay, so that's encouraging, right? We want this data to tell us how to build K-theory. And it's nice that it has coproducts and is therefore a symmetric monoidal category. And we could stop here and define at least K0 of this thing. But we have something else, which is that we have a candidate for exact sequences. Right? What's an exact sequence here? Well, it looks like this. Let's take a cofibration from X to Y. And now, if I were going to take a quotient, what would I do? I'd crush X to a point. So let's do that. Right? Take the point. This is a terminal object as well as initial, so I've got a unique map. And I know that the pushout exists. And I'm going to write this as Y mod X. Okay? And this is an exact sequence. We call this a cofiber sequence, but this is our notion of exact sequence here. Okay, so in fact, what you've done, so what are you really saying? So let me tell you how to interpret this. So that's good from our to make contact with our K-theoretic thoughts about this sort of thing, or what this kind of categorical data should be doing. But what this really is saying is that C is a category that presents a homotopy theory, right? Because we can form the homotopy category of C, right, by formally inverting the weak equivalences. That's not necessarily set theoretically well behaved. I guess this is a small category, so maybe it is. But there are fancier ways to do that. But this presents a homotopy theory, post C, and that's what the weak equivalences tell us. This is a relative category, right, in the language of that talk yesterday. But this has other data. Right? It has the data of these squares. And what are these squares? If I'm working in the category of spaces, I can't remember now if this was said in the talk on homotopy limits and colimits. But if I want to compute the mapping cone, or any of the sort of familiar examples of homotopy colimits in spaces, what do? I replace my maps by cofibrations and my objects by CW complexes. And what am I saying here? I'm saying that all objects are cofibrant in some sense. If this came from a piece of a model category, I'm saying that all objects are cofibrant, and I have homotopy pushouts. So what this is presenting is a homotopy theory host C and some class of homotopy pushouts. This is a good slogan because there are lots of ways to present that data. And any way you present that data, you are entitled to build algebraic K-theory if you are sufficiently ingenious. Okay, so let me give you some examples and then make a comment. Examples, for instance, complexes, bounded complexes of finitely generated projective R modules, right? And you got to ask, what are the cofibrations and what are the weak equivalences? We have choices for the cofibrations, but certainly one possibility is cofibrations are level-wise monomorphisms, and weak equivalences are quasi-isomorphisms, right? Or I shouldn't say right. I should say that's the truth. So, so that's one kind of example. We've already seen another example, right? I gave this before. We can take finite CW complexes, where cofibrations are cellular inclusions, and weak equivalences are, well, homotopy equivalences or weak equivalences, as you prefer. Now, an exercise is to actually prove that these things are Waldhausen categories, right? And what's the hard part of the exercise? It's usually to check this, right? You have to check the gluing. Now, it's a nice exercise in spaces, for instance, that push-outs have this property along Hurewicz cofibrations, for instance. Okay, so more generally, yes. So further example, any subcategory of the cofibrant objects in a model category with enough pushouts. And that's many of the examples that we deal with look like that. Right? And what do I mean by enough pushouts? Well, I mean at least these. Now, you might remember that we wanted smallness conditions. And in fact, in these examples, I've talked about bounded complexes or finite CW complexes. There's going to be a version of the Eilenberg swindle that's going to tell us that we want things to be relatively concise. Okay, so let me make a couple of comments about this. Because I'm picking a distinguished subcategory. I could take a single cofibrant object, and if I just take some cofibrant objects, I might not. The pushouts are in the model category, but they might not be in the subcategory. Sorry, that's just a. So what I'm saying is, you can get it if I give you a model category, you can produce a lot of Waldhausen categories by taking some class of cofibrant objects and closing them up under the pushouts you need. And of course, if you take all cofibrants, that's too big, but it is a Waldhausen category. Now, a lesson here is that there are a lot of ways to axiomatize homotopy theory. Right? Model categories are one of them, and this is another. Right? Here, model categories say I have all homotopy colimits and all homotopy limits. Here, I'm saying I just have some homotopy colimits, just the ones I need. But I have a homotopy category, and I can make sense of it. Now, let me pose a question, which we'll talk about further. Looks like maybe tomorrow, which is you can relate. So one thing I can do if I have, there's one way of getting at this homotopy theory is just through kind of the usual tools that we inherit from the theory of model categories, or these sorts of pieces of them. But another thing we can do, of course, is we can form, for C, a Waldhausen category. We can form, what can we form? We can form, the Hammock localization of C. Right? This is the Dwyer Con simplicial localization. We can form Dwyer Con And one thing that's interesting to ask yourself is, how does this, it turns out that this data is just as good as having the Waldhausen category, for the most part. And one of the things to ask yourself is, how does LHC see pushouts? Or I should say, homotopy pushouts, right? And this is a very interesting question. So it was discussed in the talk on the Dwyer Con simplicial localization that, of course, if you take pi 0 of the maps from x, the mapping space from x to y, you recover the maps in the homotopy category. So certainly I can get HO-C back out of that. And this is, in fact, a good way of doing that, because often you have good control over what these things look like. But in fact, the following is true, which is a little piece of a much more general theorem. But let me tell you the piece. And the piece is that in a nice Waldhausen category, and I'll tell you what nice means in just a second, but right now, just assume that I'm restricting certain trivial examples. X to y to z to w is a pushout. Again, I'll say homotopy, but it's a pushout if and only if there's an induced square LHC from W to Q, LHC Y to Q, LHC Z to Q, LHC X to Q. And now these maps go in the opposite directions. So Y used to map to W, so that goes like that, that goes like that, that goes like that. If this is a pullback of simplicial sets, is a homotopy, let's say, pullback of simplicial sets for all test objects Q. Okay, so why am I saying this? Well, let's remember what we talked about in the earlier part of the lecture, which was if we understand anything about algebra, we understand the category of abelian groups. And then we turned questions about kernels and co-kernels in a generic category into questions about kernels and co-kernels and abelian groups, right? Using the Oneida embedding. Well, here what I'm saying is I don't understand necessarily homotopy colimits in an arbitrary category, but I certainly understand homotopy limits in simplicial sets. And I can detect whether or not this square is a homotopy pushout in this random category by looking at the Dwyer Con mapping spaces. So this tells you that simplically enriched categories know everything there is to know about homotopy theory. Right? That's another equally valid way of talking about homotopy theory. An exercise you might think about is how can I detect weak equivalences in this way? So I should say that's an easy exercise. I don't know about easy. That's an exercise you could do given sufficient diligence. This is not easy. And of course there's a general form of this, which is that in a model category, for instance, diagrams like this, if you apply maps to a test object to any homotopy colimit, what you get is a homotopy limit of simplicial sets, and vice versa. There's a detection principle of that form. Okay, so let me tell you what nice means. How am I doing for time? Reasonably well. So what I'm going to do now is tell you what nice means, because it brings up some more homotopical stuff, and then I'm going to actually define higher algebraic K-theory. And then we will probably end, and tomorrow I'll say more about how to think about higher algebraic K-theory. But, okay, so now what does nice mean? So one of the things that you are familiar with if you work with spaces, or if you think about the example of complexes, is that any map can be factored into a cofibration followed by a weak equivalence, right? That's the thing that kind of lets you really do homotopy theory, right? I don't understand, if I have some crazy map, the quotients are probably terrible. But, I can form a cylinder, and I can use that to help me. And in fact, cylinders really maybe are at the basis. And so nice in this context, I mean, nice can mean something even weaker, but one kind of thing nice might mean is that we often assume C admits functorial factorization. So that if I have A to B, I can turn this into A to B prime to B, where the first map is a cofibration, the second map is a weak equivalence, and this is the map. This diagram commutes, and what it means to be functorial is that this is functorial in the category of arrows. So if I have commutative, this is compatible with commutative diagrams, basically. Okay, so what does this buy me? Well, great. So I can turn anything into a cofibration. Well, now I can define a cylinder. Right, so now, for instance, I can, if I have any old map, A to B, I can produce the quotient A cofibrin to B prime right, and that's my proxy for the the homotopy quotient. Right? And that's a very useful construction. Another kind of construction that you might do is imagine I have the map. There's always a generic map from the coproduct back to A. This is called the fold map. Well, supposing I factor the fold map, right? What I get is I get something that looks like this. And I'm going to suggestively write CA here, where this is an equivalence and this is a cofibration. So what have I produced, right? I've produced some object that's equivalent to A that admits two different injections from A. Well, what is that? That really looks like a cylinder, right? This is the front and this is the back. And indeed, I can use this to define homotopies. And in fact, if you look at Quillen's setup for model categories, one of the things he does, and this was talked about just a little bit in the talk on model categories, is that he defines, sort of all of the notions of homotopy that you're used to using cylinders produced like this. Now, of course, this is not, I haven't said anything about, I have said of functorial factorization, but of course this isn't unique necessarily. There could be lots of cylinders. But in familiar settings, for instance, in this example, I can always take the cylinder to be the thing we know and love. In general, maybe it's something crazy. Anyway, okay. So that's niceness. So now let me now define, march ahead and try to define Waldhausen K-theory. So of course you know how to define K0 of the data of a Waldhausen category and even K1, right? But using things we know. But I want to do something better, which is that as I alluded to a little bit, and I was going to reprise more, but I think I won't in the interest of time, there are long exact sequences connecting K0 and K1 that make you think they should be part of a cohomology theory. And so we want to define a spectrum, which is the K-theory of a Waldhausen category. So we're going to produce, the goal now is to produce a spectrum from now, this is a weird thing. I mean, think about what you're doing. This is a kind of odd thing to do, right? I'm saying take a category that knows about a little bit about abstract homotopy theory. I'm going to produce a cohomology theory from that, right? This move is now sort of internalized in modern stable homotopy theory, but when you think about it, it's a little bit strange, and it bears reflection. But anyway, so the basic idea that we want to do is the following. Let me give you the rough idea, and then I'll tell you how to actually do it, or explain why the first thing you try doesn't work, and why you have to do something fancier. So let me define, we're going to define Fn of C to be sequences like this. A0, A1, AN. Okay, so it's a sequence of cofibrations. So remember, ultimately what I'm doing is going to be building a device to help me split up cofiber sequences. And so it's maybe not so crazy that I might think about filtered objects as part of doing that. But this construction was a leap of insight and ingenuity, and so it's not so easy to motivate. But let's take for granted for a second that we want this thing. What I want to do with this is now, if I think about these as n varies, I'd like to assemble these into a simplicial object. Right? I would like to assemble yes, thank you. So what are the structure maps going to be of my simplicial object? Well, for the most part, what I can do is just compose out. Right? So the various degeneracies, most of the degeneracies are just given by composition. Right? If I have this string of n things and I compose, cofibrations form a subcategory. So the composite of two cofibrations is a cofibration. And what I have is a shorter sequence now made of cofibrations. So that's great. And certainly if I want to go up, so the face maps, those are just to insert the identity. Right? And I required already that that be a cofibration. But there's an issue, which is that what you would like to do is that the last degeneracy is supposed to be a quotient. So one of the degeneracies that we want to do is essentially amounts to this sequence is mapped to this sequence. Where I quotient through by A0. Okay, so the problem though, so great, so that seems like a reasonable thing. But this doesn't form a simplicial object. Right? Because you have a problem that cofibers are defined only up to isomorphism. And that's not good enough, right? For simplicial identities to hold, they have to hold on the nose. And so this isn't a simplicial object. But not simplicial because you have to choose the quotients. So how do you fix this problem? Well, the standard philosophy for fixing these things, maybe I should say that maybe not standard at the time, but now standard, is just make a choice to begin with and put that into the structure of the object. Okay, so now I'm going to make an actual definition, which is that the Sn of C is the category of functors from what I might write as the arrows in the poset n. Right? That's the category with n objects and a single arrow between each one, as well as the identities. And the arrows in there to C, which means sort of I have, ij goes to aij for I less than or equal to j. And what I'm going to require is that, subject to the requirements, that aii is the point that aij to ik for j less than or equal to k is a cofibration. And I'll draw a more illuminating picture of this in just a second. There's this, if you've seen this before, there's of course this triangular diagram which makes it make sense. And I'm going to require that the square aij to aik to ajk to aii equals the point, that this is a push-out. So I'm requiring that this be a cofiber sequence, that this be the a chosen cofiber of this map. And so what does that look like? So what that looks like is, so SNC has objects that look like, the point to A01, to A02, to A0n, and that's our sequence, right? That's the data of our sequence. But now I've also thrown in all these cofibers. And so I have a point, and now I have A12, and A12 is a chosen cofiber. I've required that this be a pushout. So this is a chosen cofiber for this map. And similarly, I have A13, and these are cofibrations, out to A1n, and now I have more, and so on. Okay, so what it is it's these maps and compatible choices of quotient for every possible composite in here. And those things fit together into this sort of triangular diagram. And the maps in this category are the natural transformations. So they're just commutative diagrams, right? They're maps between aij for every I and j that are compatible with the structure of this diagram. Yeah? So n is, the category. It looks like this. It's got n objects, and the arrows come from the less than relation. This is arrows in n. So this is n. Yeah, sorry. I just mean I apologize for my handwriting. I just mean the arrow category, right? It's just a way of saying I want I to be less than or equal to j, and there are maps between ij and jk if I is less than j, and that didn't work out. But ij and I prime j prime if I prime is as I is less than or equal to I prime and j is less than or equal to j prime, right? That's what I want. And okay, so now the thing you check is now that I've thrown in these choices of quotient, it's an exercise, which I'll explain at the beginning of the next lecture, but think about it now, that S dot of C is a simplicial category. Okay? And, and of course, the point now is just, if you look up here, supposing I want if I want the degeneracy that was taking the quotients, what do? I just take this part of the diagram, right? And that's great. Or it's easy to check that satisfies the simplicial identities. And if I want other parts, well, I remove a row and a column. But you should do this exercise. Okay, so now let me close with a definition of the K-theory space. I guess I'm not going to get to a spectrum. But, well, I'll assert what happens for the spectrum, and we'll pick up with this next time. So, definition, K of C as a space is equal to loops on the geometric realization of the nerve of the subcategory of weak equivalences in S dot of C. And what this takes into account is that S dot of C is, in fact, is a simplicial Waldhausen category. And the Waldhausen structure on SNC, the weak equivalences are pointwise. The cofibrations are more complicated. They're what are called Reedy cofibrations, and I'll explain that. But anyways, we can take, so what does this mean? Also, to say a little bit more, this is a bisimplicial object, right? The PQ simplices are the chains of weak equivalences of length q in SP of C. And and what do I mean by the geometric realization? I take the diagonal, that's a simplicial set, and now I take the usual geometric realization. And now I loop it down. And one of the things that this should tell you is that S dot of C is sort of like a suspension. And this we can make precise, and maybe I'll at least allude to how you make that precise. But, or more precise than something like this. But let me tell you how to get the spectrum. So that's a space. As a spectrum, Kc has nth space equal to the geometric realization of the nerves of the weak equivalences of the S dot construction iterated n times of C. So this is a, an n+1 fold simplicial object. But you can still take, if you take the diagonal, you can still take the geometric realization of that. In fact, because homotopy colimits commute, you can take any kind of realization you want. They all turn out to be homeomorphic. And this is now a space. Now, the one thing I haven't told you, so what am I doing here, by the way? I'm taking the one space and I'm looping it down. That should feel like a familiar kind of operation based on the talks on spectra, right, that you've seen. Now, one thing to say, and this will really be the last thing I say. I keep saying that, but this really will be the last thing I say, at least for today, is that you might wonder, what are the structure maps? Right? I got to tell you what those are. So it's great to give you a collection of spaces, but I need to tell you what the structure maps are. So how do I do that? Well, think about what this geometric realization looks like. We have sort of the nerve of the weak equivalences of S0 of C. That's a point, right, if you think about what S0 is. If you think about the nerve of the weak equivalences of S1 of C, what's S1 of C? That's just the objects in C, right? This is just sort of the weak equivalences of objects in C. And this is glued in. So when you take the geometric realization, this is just glued in. This is a point. How do you geometrically realize? I take an interval, and I cross it with this, and I glue the two ends to the point. Well, that's the circle, right? So I have an inclusion of this, which is just, this, which is also really just NW of C, which is the zeroth space of this thing, smash S1 into NW of S dot of C, and I can iterate that. So that was rapidly explained, and I'll say that again and in more detail. But the structure map basically just comes from thinking about the properties and the definition of geometric realization. So here's another exercise to leave you with, which is that if you take pi 0 of this object, you get k0 of C. So I will prove that next time, but that's a relatively straightforward exercise. You should think about it. Okay, and on that injunction, I leave you, and maybe we eat lunch. Yeah. Yes. That's a very good question. So the question, to restate, the question was, why did we use cofibrations and homotopy pushouts and not fibrations and homotopy limits? And I'll say two things about that. One, maybe three.